Welcome back everyone. My name is Pedram and this is where we do machine learning codes and concepts. Let's get started. Okay, let's do module number 8, K nearest neighbors, classification and regression. This is the Python part. So as always, we're going to do it two ways. We are going to do it in Scikit-learn package first, and then we will do the automated version using PyCaret. So here's where you can find the code. Go to machine learning, lectures and codes, and then scroll down, find the module 8, Python. There's a folder with 2 files in it. So this is a dataset we're going to work with, social network ads. And this is the one that we talked about it in the theory lecture as well. I know we covered the slides last time, so make sure you check them out before you're watching this one. So there are 2 files, classification and regression. And as we discussed it earlier, KNN is mostly used for classification, especially when the dimension of the data is large. We know that it's not going to do a good job for regression simply because of the curse of dimensionality. And honestly, there are better models, there are better machine learning models that we can use for regression when it comes to handling high dimensional data. So I will cover the classification first, which is mostly used. And then the switch from classification to regression is just a change in a bunch of lines of code, and that's pretty much it. So let's do that. I'm gonna do it, so you can do it in Google Colab. So actually I can go ahead and open it in Google Colab, but I'll prefer to run it on my local computer because the dataset is small and I already have PyCaret, the full version installed on my computer. And I will be using VS Code because with VS Code I can use GitHub Copilot, and it helps me a lot when it comes to the coding, right? It makes my life a lot easier. So I usually do ChatGPT and GitHub Copilot, but I really want to be in charge when I'm typing things. Then it suggests the rest of the code to me. So that's why I really would like to work with VS Code. Okay, so if you're doing in Google Colab, make sure for the PyCaret part, you're going to do pip install PyCaret. But I already have it on my VS Code. So let's open it up and let's take it from there. So let me close this one. I hope the font size and everything is good. So let's starting with the KNN classifications. Again, I have an environment already created for PyCaret. So I'm going to go ahead and pick that one. And we should be good to go. So let's run this. So let's import the relevant libraries, NumPy, Pandas, Matplotlib, Seaborn for visualization, and we're going to ignore the warnings. So we're going to set the random state to 1000 because again, this is going to be used when you're splitting the data, when you're using some random number for search and etc. So if you want to get the exact same numbers as I do, so make sure that you use the random state is equal to 1000. Then we're going to import the data set from the GitHub. And basically this is a social network data set. If you look at the head of it, this is a very simple low dimensional data. That's why I expect our KNN to do a good job, because again, the dimension of the data is small, and no matter how nonlinear the data set, the relationship, the pattern in the data is, the KNN should do a good job. So we literally have only 3 features, right? We have gender, which is a dummy variable, age, continuous random variable, an estimated salary, another continuous random variable, and this is our target, which is purchase. We want to see if someone is purchasing a vehicle or not, and this is basically social network ads data set. User ID is not going to be informative, so we're going to drop it right away. So here only 400 observations, 3 features, 1 target variable. That's pretty straightforward. So I'm going to go ahead. This is a classification task. So I hope that you remember from our logistic regression Python part, the very first thing that I would love to do is to look at the distribution of the target variable and basically look at if it is balanced or imbalanced. So we have 64% class 0 and 35%-ish class 1, which is pretty good. This is a relatively balanced data set, and I'm going to go ahead and use accuracy when it comes to, for example, doing cross-validation, comparing the different hyperparameters of the models, and etc. Okay. All right, so we are going to quickly check if there's any NA in the data. So all good. We're going to go ahead and drop the user ID again because this is not informative here. Sometimes IDs are informative, but this is just some random number, so this really doesn't make a huge difference. So we're going to drop it. Then we are going to make sure that our categorical variables are changed into dummies. And then I can see that because gender was 0, 1, it's going to change it, and purchase was also 0, 1. It's going to change this gender to a gender male. So we're going to rename it to just male. And then, yeah, basically this is the pre-processing part, right? And now the data set is simply purchase or not, and age is estimated salary and male, okay? Yeah, pretty straightforward. We can look at some summary statistics, and basically we can look at correlations. We can look at the pair plots. Yeah, again, typically in real world application, you know, for a bigger project, we don't have the luxury to see the pair plots like this, because what if you have 1,000 features, right? You know, you don't want to do the pair plot unless you're curious about some of the features. You want to say something. You want to have something to say when it comes to interpretability of things, and then you might want to go ahead and do the pair plot for those variables of interest versus the target variable, right? So here there was only 3 features. No, it really doesn't take too long, so we went ahead and did it anyway. So this is our age distribution, and the colors are of course the target variable, right? So we do the target variable as the color code, and then this is going to help us to distinguish how the data is spread out in terms of in this case purchase or not purchase, right? For example, if I look at here's an interesting observation, right? So we can say look at your age and estimated salary, and then if they're purchased or not. So it seems that, you know, the younger ones with lower estimated salary, they end up not purchasing an SUV, and the older ones with higher salaries end up getting an SUV. So this is interesting observation. So to me, when I look at this plot or even this plot, well, let's see. Yeah, so because there's a clear distinction between where these dots are located. So I would guess that KNN is going to do a great job. So again, pair plots can be informative for intuitions like this. All right, so this is KNN, K-nearest neighbors classification. We are going to go ahead and calculate the Euclidean distance between observations, and whenever we're doing some distance metrics between points in the data, we should do scaling. Otherwise, one of the features is going to have a dominant effect on the other one when it's come to calculating distance. So again, this is typically the case for KNN, the models, because we are clearly calculating some distance. Either it is Euclidean distance, Manhattan distance, whatever type of distance it is, we need to make sure that we are scaling the features. Okay, so, and obviously we don't need to scale the dummy variables. So here, just for simplicity, I went ahead and scaled everything. And then down the road, I make sure that the dummy variables are scaled back to 0, 1s, right? So we call the scale version df_sc. This is the scale version. Here's the head of it. And obviously I need to return this purchase and male back to 0, 1s. So this is what we're doing here in this cell. So we're borrowing the male from the original data set and then add it to the scale version, and the same story for purchase. So if I look at the head of this new data frame, obviously the male and purchase are going to be dummies, and age and estimated salaries are continuous random variable and are scaled. Okay, great. So I think everything is ready for us to basically build the model and train it. So typical machine learning steps: this is a target variable, this is our feature space, again 3-dimension, train test split, 80% test, 80% train and 20% test. The reason we are doing 20/80 and not 30/70 is that we only have 400 observations, right? So I need more training observations to make sure that the model is learning something. All right, so we are going to go ahead and create them. We can take a look at the head of the train set, and remember, if you're using the same random state as mine, you will see these observations as indices, observation numbers as indices, okay? Okay, so let's go ahead and import from Scikit-learn neighbors. As the name suggests, this is a module. And then this is a class. We're importing the neighbors classifier, K-neighbors classifier. And so this is going to be our model, right? So we're going to look into the documentation in a second, but let's see how we can build this model first. So we just need, I'm going to go ahead and create an object. This is my classifier. I can call it KNN classifier. And then obviously we have a parameter, which is number of neighbors. So we're going to start from 20. And then once you have an object, like any other machine learning model, you can use fit in the train set. So now the model has been trained. That's pretty much it. Then we're going to make some predictions and basically use them, right? But before that, I want to definitely share with you a couple of things. One, the distance metric we are using, and what are the other parameters, right? So let's go ahead and open this one. So this is the Wikipedia. Let me actually close this one. I'm going to go ahead and do Scikit-learn documentation, KNN, let's say classification, right? Classification. All right, so let's go to the first link. This is a Scikit-learn documentation and see what are the features, right? So the parameters. So obviously this is our classifier. We already talked about two parameters in the video, in the theory lecture. The most important one was the what is K, number of neighbors, number of observations in the neighborhood, and what is the distance metric, right? So we already covered those things theoretically, but let's see how we can, what are the options in this class, right? So number of neighbors, by default, this is your K. By default, it is set to 5. Obviously, you can set it to whatever number you want. Here we started at 20. Then we have weights. So again, these are the parameters that you can play around with, right? So weights by default is going to be the uniform. So it means that every single observation is equally weighted, but you can change the weighting, right? For example, you can say distance. If I say distance, it is going to be inversely related to the closeness, right? So basically, it will be something like this. The closer neighbors of a query point will have a greater influence, right? Compared to ones that are further away. So what does it mean? It means that, let me show you. For example, we have something like this. So this is our query point, the red one. We are trying to classify this one. So obviously it says that if the weighting is based on distance, this observation is going to get a higher weight compared to this observation. So that's pretty straightforward. But we're going to leave it as default. We want to make sure that all the observations have the same chance. So we're going to call it uniform. And what are the other things? So we have, this is the searching algorithm, right? For the searching algorithm, we have auto, which is obviously, we're going to leave it to auto because it's going to make sure that it's using the best algorithm to just save some time. But the options are ball tree, KD tree, or brute force, right? So obviously the brute force is the one that goes and calculate the distance between all the points in the data. But as the name suggests, this is literally, so for example, if I want to classify this red dot, so I have to go ahead and if I use brute force, so it's going to go ahead and calculate the distance between every single observation in the entire space, right? And again, this is very simplistic 2-dimension with 10 observations. In real world, imagine you have 10 dimensions and thousands of observations, and you get the idea that brute force is going to take longer, right? If you want to calculate all the distances between all the points, right? So how can we optimize it? We can use other techniques called ball tree or KD tree. This is pretty straightforward. The idea is that instead of calculating the distance for all of these dots, so for example, imagine my red dot was here, right? And then I don't need to go all the way to here. I can just split the space into some other points. So for example, I can look at the median. This is what KD3 is doing. I can look at the median for x1, median for x2, and then say, hey, first check out this neighborhood and then go to the other neighborhoods if necessary, right? So that's the KD tree. The idea of ball tree is the same thing. Instead of working with squares, it's working with balls, right? So it's going to split the data. Again, the details, you don't need to be worried about the details. You can easily Google it, or you can use ChatGPT to explain it a little better for you. But the idea is simple. Instead of going over calculating all the distances between the points, between the point of interest and all the observations, we're going to split the data and do the search more efficiently, right? All right. So then, again, if you're using other algorithms, the leaf size is going to be important. So because we haven't talked about decision trees yet, I'm going to postpone this discussion when I cover the decision trees. But the reason that you're seeing this leaf size is that if you're using KD tree or ball tree, then you're talking about a tree down the road. And then the concept of leaf and things like that is going to become important. But for us, practically speaking, we're going to let it leave it to auto. And then obviously it's going to start from ball tree and then try to look at the KD tree or brute. And depending on the nature of the data, it's going to pick the best one. All right, so let's see. P is an important one, right? Because this is our distance metric. So let's go back. Yeah. By default, P is equal to 2. And if you remember, we talked about this Minkowski metric, right? So this is our Minkowski metric. So we talked about this equation in our theory lecture. So, and now we're saying that if P is equal to 2, this thing is going to become square root of something to the power of 2. And this is our simple Euclidean distance, right? So yeah, by default, we're using Euclidean distance. It means that if you're looking into basically two-dimensional features, we're talking about circles. So distance metric is going to be circles. Okay, and actually let me show you something. There's a cool visualization here. When P is equal to 2, this is your in two-dimensional space. This is how the neighborhood is going to look like. If P is equal to 1, this is how it's going to look like. This is your Manhattan distance. P is equal to 0.5, P is equal to 0.25, so the shape is going to change, right? Or P is equal to 4, and etc. Or P is equal to infinity, we get a square, right? Yeah, so let's go back and see what else we have in the documentation. So many of these parameters are going to be shared for regression, so I'm not going to repeat these things when it comes to the regression part, right? So let's scroll down, let's see what else we have. We have metric parameters, metrics. So we talked about this one, right? Minkowski and P is equal to 2 is going to give us the Euclidean distance. Yeah, that's pretty much it, right? So this is it. These are the parameters of the model. If you scroll down, you see some simple examples. Again, the documentation of Scikit-learn is very, it's good. And then this means that you can simply rely the outputs of ChatGPT when it comes to generating these codes for you. Yeah, this package has been around for years and it's pretty very well documented, so, and it's pretty straightforward. Okay, so obviously we're going to go ahead and create an object and then fit and then make some prediction. That's simple. Okay, so, and these are the methods you can get off of that object that you created, right? Imagine this is your object, which is a model container, well, let's say a model object classifier. You can use fit, you can get the parameters, you can look at the neighbors, you can make predictions, you can make probability prediction. This is also interesting, right? Because remember, in the theory we talked about it, the outcome of KNN classification is also probability. So this is great news. It means that this is one of those probabilistic models. It means that it's going to generate some probability for you. For example, it's going to give you the odds of this observation being class purple or being class, let's say here A, or yellow here, which is 2/3, right? So the odds that this red one, if K is equal to 3, is going to be 2/3, and the odds that this red observation is yellow is going to be 1/3 if K is equal to 3, right? So that's where you can grab those probability. All right, so I think we're good. Let's go back to the VS Code. Okay, where were we? So we created an object, we said neighbor is equal to 20. Now we can remember those methods. We could do predict or predict probability. So I'm going to create something called y hat. These are my predictions, and the predictions are going to be 0, 1s, and prediction probabilities are just some probabilities, right? And obviously it's going to be the probabilities of class 0 and 1. So let's, if you have 2 classes, if you have 3 classes, it's going to be 0, 1, 2, and etc. Okay. So here is what the output of the predict probability is going to look like, right? I'm going to show you the first 5 predictions. And as you can see, this is an array with 2 basically components. The first one is going to be the probability of 0. The second one is probability of 1. So this is probability of purchasing an SUV, right? And this is a variable of interest for us in terms of target variable. What is the probability of buying an SUV? So that's why we're going to pick that element. So it's, give me all the rows and then the first column. So that's the probabilities, right? So then the next thing we need to look into is basically say, what is the range of that probability, right? So it's going to be obviously between 0 and a large number, right? So these are rounded up to 2, 3. So if I just remove this round, it's going to be 0.95. because this is the max. And then another important thing for classification in general is that when you have a model that can predict probabilities, definitely go ahead and plot the histogram, right? So here's the histogram, and it seems that probabilities are spread out between 0 and 1. This is great. Now, if I use the default threshold value of 0.5, it's going to be okay, right? Because the data set is also balanced, and I'm very confident reporting some metrics like accuracy. All right, so, but just for the sake of presentation, I'm going to go ahead and create the probabilities. Well, I'm going to go ahead and create some predictions when threshold is equal to 30% and some predictions when threshold is equal to 70%. This is pretty much the same similar to what we did for the logistic regression, right? So we say that if the probabilities are greater than 30%, call it 1, otherwise 0. And if it is greater than 70%, call it 1, otherwise 0. We can put all these predictions in a nice data frame. So this, I'm going to call it my prediction data frame. Actuals, predictions, these are the probabilities. And then this is basically when the predictions when threshold is equal to 30%, predictions when threshold is equal to 70%. So I can go ahead and hit this data frame. Yeah, there you go. So these are the probabilities, and then 30%, 70%. Okay. Now the next thing is we have trained a model. We want to look at the performance in a test set, obviously, right? I'm going to go ahead and import some metrics: accuracy, recall, precision, F on a score. Again, in this case, we are pretty confident with the number we get from accuracy. We can look at the confusion matrix, classification report, ROC, AUC score, right? So we have done this extensively before, so it's gonna be easy to just go ahead and use the code and then interpret the results, right? Starting with the confusion matrix, so these are good numbers, right? Remember, on the diagonal, these are good numbers, true, negative, true, positive, and then the bad numbers, 4 and 9. Right, true, false, positive, false, negative. And then based on these 4 numbers, we can have a bunch of metrics, right? So there's this built-in function in Scikit-learn called classification report, which we already imported it here. We can look at the outcome, the predictions, right? So it seems that our model is doing a decent job. And in general, right, the accuracy is 80%, 84%, and this is precision for class 1, which is 85%, recall for class 1, 72%, and F on a score. So let me quickly interpret this one and maybe remind you, those who probably forgot what these numbers mean, right? So starting with the support, so we have 80 observations, 48 of them are class 0, 32 are class 1. So this is in a test set, right? Remember, we split it 80-20, so 20% of 400 observations. So this is where the 80 is coming from. Almost half-half, almost 60-40. And then we can say out of these 48 observations, so let's start with the precision, right? So what is precision? It says that for those that model predicted 0, 83% of them were correctly predicted, right? So this is not bad. For the observations that the model predicted 1, 85% were actually 1, right? So this is good. So this is how we interpret precision. How do we do recall? Recalls, we are going to look at the actuals, right? We say for those observations that in reality they were by an SUV, they were 1, we ended up predicting 72% of them correctly, right? And this is recall for class 0. Basically says that for those observations that ended up not buying in reality, the model recall picked 92% of them, right? So, and then if you want to connect these numbers with the classification report, it should be pretty straightforward. I'm going to do one of them, for example. Let's do recall for class 1, right? So recall for class 1, we are basically here for those that were actually, so this is what I'm here, for those that were actually purchased, what percentage was correctly predicted, right? So 23, or correctly recalled. So the answer is going to be 23 divided by 23 plus 9, right? So this is my recall for class 1, so 72%. That's where you're seeing it. And obviously F on a score is going to be harmonic mean between the two, right? The harmonic mean between these two numbers is 87, between these two numbers is 78. Then we have accuracy, then we have macro accuracy, weighted accuracy, macro average, weighted average, right? So macro average is simple average between these two numbers, 83 plus 85 divided by 2, 92 plus 72 divided by 2, 87 plus 78 divided by 2, right? Weighted average is weighted by the support, right? By the frequency in the data, right? So this is going to be 83% multiply the weights, 48 divided by 80, plus 85% multiply 32 divided by 80. Okay, I hope you're following. All right, so I'm gonna, just like what we did in logistic regression, let's put it all together in a nice function. I'm gonna call it defining my own KNN report. So feel free to play around with this, right? So I'm gonna go ahead and say, this is my KNN report, because later on, I'm gonna plot the, basically, hyperparameter, the different values of K for, let's say, accuracy cross-validation, and then just decide what was the optimal value for my hyperparameter K. Okay, so that's why I need this function. And this is nothing fancy. We have done this all in the previous cells, so I'm just putting it together, right? So feel free to pause the video and then make sure that you understand every single line. But again, nothing fancy here. So if you're training an object, we're creating an object, we're training it, we're making some predictions, and we are defining our threshold. So this is going to be an object. This is going to be one of the features of the object of the function, right? And weights, I'm going to use uniform, but we have the we have the option to change it if you want, right? Then we're creating this report. Now if I run this simple line, oops, I haven't run the function yet. So now we can run this line. Now there you go. We are going to pass some data. If k is equal to 3, this is accuracy. If k is equal to 4, we have a different accuracy. If I go ahead and change the threshold to other numbers, obviously the numbers are going to change here. So for example, if you, what is your recall? Well, recall is already high. It's 95. But if I want to make it even higher, I can reduce the threshold to avoid false negatives, right? So it's going to increase the recall for me. So we went from 91 to 94. If I want to increase the precision of the model, depending on the task, right? I'm going to increase the threshold to make sure that we are avoiding too many false positives. And if that's the case, I can run it and then see, oh, there we go, precision is 93. And obviously, if you use PyCaret is going to give us a precision recall curve and give us that optimal value for the threshold as well. But here we're going to go and use just 50%. So some quick questions. What will happen to my KNN report output if threshold is 0.3? What about 0.7? So we already answered that one, right? Again, I encourage you to pause the video and try to answer it one more time. Now try weights is equal to distance. What do you conclude? Again, here, if I go ahead and change the weight to distance, okay. So just take a screenshot of these numbers. Okay, now let's see what changes, right? So maybe pay attention to these numbers, and then the overall accuracy, which is 0.91. So let's see. Okay, it changed, but not dramatically, right? Especially, again, we have very few observations, so that's why these numbers were a little sensitive. But in this case, because these two, either we did weighted or distance, we did uniform or distance kind of weighting, because it didn't make a huge difference, it means that there's not much sparsity in your data, right? So they are close enough together. And why am I confidently saying something like this? For two reasons. First of all, these numbers didn't change that much. And second of all, remember, we did this pair plot. And we looked into the pair plot and said, okay, there's no, at least there's only two continuous features, right? So the data set is pretty, basically pretty dense, right? So I don't see any sparsity in this data set. So that's why confidently I could go ahead and either use uniform or distance. It doesn't make a big difference. All right, so let's see what else. ROC, right? So this is area under the curve, and we have done this before last time, so I'm not going to spend time here, but just remember, we are comparing the no-skill model. This is a no-skill model versus your model. So in this case, our model is KNN, right? And the area under the curve is literally area under these curves, lines, right? So for example, area, this is go from 1 to 1. So area here is going to be 1 divided by 2, right? So it's going to be 50%. So 50% is the AUC of a random model, and then the higher the better. So in this case, we're going to get 94%, and which is great, right? And do I trust this number? Yes, because my my data set was balanced, right? And just a quick reminder, what is ROC? It's basically plotting false positive rate versus true positive rate, both, and then it's for different thresholds, it's calculating those numbers and then making a plot and calculate the area under, right? So for the no-skill is a random model. So here I'm gonna say if the model predicted 0 for everything, no purchase for everything. So this is a random model. If I go ahead and change to 1, the model is predicting 1 for no matter what. So there's gonna be no change in this blue line. Just pay attention. So I run it, no change. So this is a no-skill model. So it's always predicting either 0 or 1. It really doesn't matter. Okay, so are you excited about this high AUC? Yes, because the data set is balanced. Cross-validation. Why do we do cross-validation? Remember, we do it for 2 reasons. 1, for tuning the hyperparameters in the model. 2, for coming up with a estimated value for performance of the model in the test set, right? So we are gonna do it both ways. We want to say, okay, for example, this is the accuracy of the model, which was 90%-ish when k was equal to 4. Yeah, 91%. For example, we want to estimate that number, so we can do cross-validation. Or if you want to say, who says that k is equal to 4 is better? So can I just do random numbers and see which one is better? So this is one way. Another way is to obviously do, well, interesting. There is no change here. Let's do 20. Yep, there you go. The other way is to make sure that we are plotting the cross-validated accuracy versus, let's say, model complexity parameter, which is k here. So we're going to do this. We're going to plot this. We're going to replicate this. Okay, so scrolling down, let's go ahead and import the cross-val score from Scikit-learn model selection module. And just remember, these are the metrics, right? So the metrics are these, and then here I'm happy with the accuracy, I'm going to pick that one. But they're different, so you can do F1, you can do precision, recall, you name it, right? So actually I can leave it like this, that's fine. All right, so let's do accuracy cross-validation. We have to pass an estimator. This is what we created, KNN classifier, nothing fancy here. And then pass a train set, 5-fold scoring method accuracy. So this is going to be give me a 5 number, and I'm interested in the error rate, for example. So I'm going to do 1 minus accuracy. So these are the error rates, right? So 12.5%, 12.5%, 4.6%, and etc., right? And then I can look at the standard deviation of the error rate as well if I want. So this is what we were talking about in the theory lecture as well. And then we can go ahead and take the average of these 5 numbers and then round it up. So this is our error rate. So the error rate is just 10%. The cross-validation error rate, right? So if the error rate is 10%, what is the accuracy? 90%. So this is an estimation of my 90% here up there, where we calculated 90%. It was again, depending on what k you're using. I think we were using k is equal to 20 by default. Yeah. All right. So this is my KNN classifier. Yep, there you go. Now let's talk about choosing k, right? So how can we pick up the best value for our hyperparameter? Remember, hyperparameter is not trained first. We have to pick some random number. So we pick 20. Now, once the model has been trained, we're going to look back, say, hey, was this the best number? Let's figure it out. So that's why we're doing cross-validation, right? So I'm going to go ahead and create an empty list, error rate. So we're going to stack a bunch of these error rates on top of each other. So let's say specifically 50 of them for 50 different values of, let's say this is 49 because it doesn't include k. 49 different values for k. And again, this for loop is nothing fancy. We're going to create an object for different values of I. We're going to train it, and we're going to append the error rates to this list, right? So what are the error rates? So here we had the accuracy. We didn't need to define it manually, but here we can define it manually, right? If you remember from the theory lecture, we can say wherever the actuals are different from predictions, right? So wherever the actuals are different from the predictions, the model is making a mistake. So let's take the average of all those mistakes. So this is going to be your error rate, and that's it. So I'm going to have error rates, and then I can plot it. So this is the error rate in the test set. Okay. There you go. So this is error. Why is it in a test set? Because I'm using a test set. Later on, we're going to do the cross-validated version of that, right? So yeah. So this is error rate versus test, right? If I want to decide what is the best value for hyperparameter using test set, using accuracy in the test set, which is not necessarily correct, but what is that number? You might want to say it's any number between 5 and 15 is giving me the same small error rate, so that's going to be the case, right? But here I have a very important question for you. I want you to pause the video and think about it. So imagine we decided to pick the hyperparameter of the model K based on the performance in the test set, accuracy in the test set. Imagine we did that, right? Then we know that for K is equal to 5 to 15, we get the same number. So which model do you pick? K is equal to 5, K is equal to 10, K is equal to 15? Yes, K is equal to 15, because if you have a simpler model compared to more complex model, remember, if K is smaller, the model is more complex. If K is equal to 1, the model is most complex. So here the model is more complex compared to here. So when you have two models, not two models, they're same models. This is two, let's say, model architecture. When we have two different architecture of the same model family, you pick the one which is simpler, right? Because yeah, the simpler the better if you get the same performance. Okay, so this is going to be the winner. But what is wrong if we rely on the error rate in the test set and use K is equal to 5 or 15? So we know that we're going to pick 15, but what is wrong with that? You're cheating, right? Because you're tuning the hyperparameter with the data that it's in the test set. So when it comes to training the model, tuning hyperparameter, you want to make sure that absolutely you are not using a test set. So that's why we have to do cross-validation, right? So what is wrong if we plot error rate versus K and using the train set? For train set, it's even worse, right? Because obviously when K is equal to 1, I'm going to get the smallest train set, but what's the point? This is absolute cheating. So what's the solution? Cross-validation. So that's why we're going to create here just for fun. Typically, we only need to plot the cross-validated error rate versus K, but here we're going to do both of them, right? So you already saw this one above, right? Error rate in the test set, but I'm going to create it again. So put it in a nice for loop. So train a model. So create an object, K neighbors classifier, and then train it using a train set. Now here's the cross-validation version. So I'm going to say, go ahead and give me the accuracy from this cross-val score. When I have the accuracy, the error rate is going to be 1 minus accuracy, and I'm going to take the average, right? So this is my error rate cross-validated. What is error rate test? What we just created up there, right? Whenever the actual is different from predictions, go ahead and sum them up, take the average. Okay. All right, so this is I'm going to put it in a nice data frame for visualization purposes. So this is my data frame. I have error rate cross-validation, error rate test. I can go ahead and use line plot. You can, for example, you can set the index to be equal to K and then do the seaborn, whatever. Again, when it comes to visualization, just do whatever you're more comfortable. You can do Matplotlib, you can do seaborn, you can do ChatGPT, honestly. It really doesn't matter. Yeah, there you go. This is what we have seen before. This is the accuracy in the, well, actually it's error rate, sorry. This is the error rate in the test set. And this is the error rate. The blue one is the error rate cross-validated. So if I want to pick the best value for hyperparameter, I'm going to look at the blue line, not the orange one. If I look at the blue line, what is the optimal K? This is the optimal K because it's giving me the minimum error rate in the cross-validation set. Okay, it seems that K is equal to 9. So when K is equal to 9, let's go ahead and use it. There we go. This is our best performer model for KNN classification. Okay, then last but not least, excuse me, I'm gonna do some visualization, right? So what's the goal? The goal is to, let's see, do we have it here? Yeah, we didn't talk about it here. So I want to plot the decision boundaries, right? So we talked about the theory part, but let's see how can we do it in practice. So I'm going to do visualization, and because we want to do it in 2-dimension, I have to get rid of one of the variables, and I'm going to obviously I'm going to get rid of the one which was categorical, which was gender, male or female. So I'm going to work with this these two features, age and estimated salary, and the target variable is going to be purchase. So because down the road we're going to use PyCaret, honestly, don't worry about it if you don't want to follow this part. But because in PyCaret with one line of code we can do the decision boundary, so that's the beauty of using PyCaret. But here, if you want to just follow with me, make sure that you understand we're using only 2 features. So it means that if in reality you have 10 features, you cannot randomly pick 2 of those features. So we have to use some techniques called principal component analysis or some other dimensionality reduction techniques to go from 10 dimensions to 2 dimensions, and then use those 2 dimensions to plot our decision boundary in 2 dimensions, right? But PyCaret is going to do it automatically for us. So again, we have seen all these things before. I'm scaling the features, I'm basically training the model, I'm making some predictions, and I'm plotting those decision boundaries, right? So with, let's see, what was k? We picked k is equal to 9. With k is equal to 9, this is a decision boundary. It's going to take some time. And you can see this is only 400 observations. And obviously we are going through all the numbers between, let's say, -3 to 3, and we're creating a mesh, and we are calculating all those distances to come up with this decision boundary, right? So this is a decision boundary. So anything on the red shaded area is going to be classified as 0. Anything on the green shaded area is going to be classified as 1. And wrong colors on wrong background are misclassifications, right? So this is misclassification, this is misclassification, and etc. So the model will be trained using train set. So it means that this is going to be my decision boundary going forward, right? If I remove all these dots and then throw the test set, the decision boundary is not going to change, because remember, the decision boundary is coming from the training part, right? So that's why if you're overfitting here, then it's going to look ridiculous for the test set, right? So here this is, and as you can see, this is, this is super nonlinear, right? If I wanted to use linear classifier like logistic regression, I don't know, maybe it could do something like this, or I could spice it up with some nonlinearity like this, right? But I would never get something like this, right? So this is the power of KNN. So I'm going to remove all these dots and then throw the test set, but with the same decision boundary. This is how it's going to look like, right? Do you see that? So just, I'm going to do a quick back and forth and you compare. So this decision boundary is going to be exactly the same. You see? But I'm throwing some new data at it and then report the metrics. So for example, what is the metric? It's going to be this one. These are the good numbers and bad numbers. There's only 5 misclassification, right? Can you spot them? Yeah, these are 1, 2, 3, 4, 5. Okay, so let's see. Yeah, I just for the learning purposes, I'm gonna go ahead and change this k from 9 to 1, and I'm gonna let it run. And I want you to, I haven't pressed Shift Enter yet. I want you to pause the video and think about it. What will happen? Okay, so we are gonna see a funny decision boundary, because remember in the theory lecture we said if k is equal to 1, it's going to be most complex, right? When k is equal to, let's say, larger number, it's going to be least complex, well, less complex. There you go. So this is absolutely overfitting, right? And as you can see, it's doing a perfect job on the train set. What is the accuracy? 100%. Do you see any misclassification? I cannot spot one. Can you? Yeah. So the accuracy is 100%. But is it good? Well, this is 100% in train set. If I remove all these dots and then throw the test set at it, see how ridiculous it's going to look like? And give it a second. So it's going to create, the decision boundary is going to be exactly the same, but we're going to using some other, yeah, there you go. So this is ridiculous, right? So obviously there's some misclassifications, but why this should be red in the, and then, so that this is the concept of overfitting, right? So your model is overfitting, and this is a ridiculous decision boundary. And if I just look at the confusion matrix, we have 12 misclassifications now compared to which was 5 for k is equal to 9. All right, so that was pretty much it, the scikit-learn part. Now let's cover the PyCaret. Okay, so PyCaret, make sure that you have the documentation open and ready. So this is the PyCaret documentation. This is Scikit-learn for, well, this is Scikit-learn in general, and this is the PyCaret model container. Again, if you're a beginner, I absolutely want you to read these documentation at least once, and then to realize what, look at the source code, what is going on behind the scene and things like that, okay? This is a good practice. So for example, here we're going to go to this is PyCaret model container, right? We're going to go to classification, and then we should be able to find our KNN here. So our KNN, K nearest neighbor classifier. Well, actually, yeah, this is our K neighbors classifier, which is directly coming from Scikit-learn, right? And then if you scroll down, you should see some tuning hyperparameters. So the tuning hyperparameters for, so just be aware when you're doing PyCaret kind of modeling, you have to be aware what is the set for tuning hyperparameters. So for example, now we know that when we read the documentation or when we look at the source code, we know that the K in the PyCaret goes from 1 to 50. So if you think that your model is looking into K is equal to 55, 60, 100, you're wrong, right? So you have to make sure that, so that's why I want you to use Scikit-learn. So for practical purposes, we use PyCaret to just quickly figure it out what models are going to perform better for your data set. And then once you pick the top 5, go ahead and play around with the hyperparameters using Scikit-learn. Okay, so going back to the VS Code, I don't need to go ahead and install it, but if you're doing it in Google Colab, run this line. Okay, uncomment this one by removing this £. And I already am in the PyCaret environment. This is, let's check the version 3.1 by the time I'm recording this video. And yeah, let's go ahead and import the data set. This is the same data set, but unprocessed, let's say. From PyCaret classification, import everything. And then let's go ahead and set up an experiment. This is a data set. The target is purchased. This is my target variable. Are you going to ignore some features? Yes, I'm going to ignore user ID, my session ID. This is just a random number. Train set 70-30. We can do 80-20 to be consistent with what we had before. Pre-process, yes. Categorical features, gender. So I'm going to say this gender that you're seeing here is my categorical features. If the data set is something as obvious as this, you know, some strings, you don't need to specify it. PyCaret is smart enough to figure it out. But I think it's a good habit that you get, you develop to just specifically tell it to your PyCaret that, hey, this is my categorical variable. We can go ahead and set up the experiment. And once the experiment is set up, we're done. The rest is just a bunch of simple lines of code, right? So the available models, I'm not gonna run all the codes because for PyCaret it's gonna take some time, but I'm gonna walk you through. Feel free to just run it from your end. So the models, when it comes to classification, PyCaret, we have seen this in logistic regression. I'm gonna review it quickly. Logistic regression, there you go. So logistic regression, KNN, naive Bayes, decision trees, and etc. SVM, you name it, random forest. Yeah, there you go. We have XGBoost. So I think if you're installing the light version, which is this, if you do pip install PyCaret, this is going to be the light version. If you want to get the full version, you have to do pip install PyCaret full. Okay. And if you do the light version, you will not see cat boost. I believe you will not see light GBM2, but yeah, you double check it. XGBoost was added to the light version recently, so I really like it. For 3.0, you don't need to install XGBoost separately. On Windows and Ubuntu, if you want to do it on Mac, no, on Mac you have to install it separately. Sorry. So PyCaret is one of those packages that Probably if you run it on Ubuntu or Windows, it's going to give you less headache compared to Mac, especially if you want to do M1 or M2 chips. Okay, so then the rest is pretty straightforward, right? So where's our KNN? Go ahead and create model, KNN, that's it. So we have done these things before, but if you're curious, please check out the documentation of PyCaret. Go to PyCaret documentation. I put the link on the notebook, and then go to classification, scroll down, what are the available functions? So create model, how do I do create model? This is one way to navigate through this gigantic documentation. Another way is that go back, I don't know, just use the first link, copy this link, and if you have ChatGPT, the browser version, or Google Bard, or I don't know, the browser version ChatGPT is, it's paid subscription, but you can say, hey ChatGPT, use this documentation, which is the latest version of PyCaret 3.0, and then answer my questions. Now, then ChatGPT or any other large language model, by the time you're watching this, I don't know what you're using, but the prompt should be something like this. Go ahead and use this link, make sure you use the latest documentation, and then generate some consistent code in Python, which is, again, consistent with the documentation, the latest version. Okay, so this, again, coding has become a lot easier these days, and that's the trend going forward. It's going to become even easier than this. I think eventually we get to a point that here there's a microphone button, and then you can push it, and then you can say what you want to do, and the code can be created. We are not far away from that thing to become reality. Okay, so this is KNN model. By default it's going to do 10-fold. Oh, did we set up the 10-fold? I think we did. Well, we didn't specify. So the default K for number of folds for classification is 10. So that's why you see 10 numbers here. And what do we have? Accuracy. This is a number that I'm interested because the data set is balanced. So 78%, I'll take it. So this is KNN. Can I make it better by tuning the K? Let's actually, I want to show you something. So let me run this. Yeah, because I want to show you something. I want to get the parameters and see what was the default parameter of this model, right? So let's actually try to do it for this. So I have GitHub Copilot. I haven't tried it, but let's say let's get the parameters of KNN model. Let's see what it suggests. It's not a good suggestion, but anyways, so I can do there you go. When I do KNN dot, it gives me the get params. So this is going to be the parameters, and so the algorithm is auto metric Minkowski. So p is equal to 2. We are using the Euclidean distance. So by default, it's using k is equal to 5, right? We already knew that our optimal k was 9 using Scikit-learn. So here, let's see if we use a tuned version, what value we get for k, right? So I'm going to do tune model KNN. You have to make sure that you have created this model already, which we did, right? And then I'm going to do tune model KNN, and then we can get the parameters, right? We can get the parameters either by calling tuned KNN.get parameters, or we can plot the parameter plot, right? So if you do the parameter, let's see, number of neighbors, was it again 5? Okay, that's fine. It was different from Scikit-learn, but let's see. I'm gonna try it one more time. We were able to improve it 78% to 77%. Not necessarily, right? Yeah. Again, this is cross-validation, right? We use 5-fold. This is using 10-fold. So these numbers are fluctuating based on that. Right, but we ended up with k is equal to, let's see, 5 here, which is, again, this is different from what we got in Scikit-learn, but it really doesn't matter. You look at the performance. Eventually, you're going to pick a model that performs better in the cross-validated data or test set if you want to compare it with other models. All right, so we have done the rest also before. Now, just plotting the, let's look at the AUC ROC. So this is my ROC for both classes, right? It's 94%. And then if you scroll down, so this is our threshold plot. And this is what I was talking about at the beginning of this lecture, right? What is the optimal value of that threshold, maybe? So it's plotting the recall precision F1 based on different threshold values, right? And obviously, if we increase the threshold, the precision is going to increase and recall is going to decrease. And this is what we're seeing here, right? If I decrease the threshold, the recall is going to increase, precision is going to decrease. There's a sweet spot somewhere there, which is shown by this vertical line, dash line, which is 40%. So if you want to come up with a threshold which is going to give you a good balance of all the performance metrics, go with 40%. If for your problem it really doesn't matter, you want to look at the accuracy and then the data set is balanced, go with the default value of 50%. Again, this is very subjective and depends on the task that you have on your hand. We can look at the precision plot, the precision recall plot, PR plot, and then we know this is a great one. What I'm seeing here is great because look at the average precision is 85%. So it says that for different values of recall between 0 and 1, if I calculate the precisions and take the average, is 85%. So our model is doing a pretty good job in terms of making predictions for class 1, which is purchase SUV. All right, so 85% of those predictions are correct. All right, so this is the narration, the narrative. If you didn't understand what I said, just go ahead and read this one more time. And then we can look at the confusion matrix. So there's nothing fancy here. We did it with Scikit-learn as well. We can look at the classification report. Again, same story. Support, precision, recall. So it's just rotate the columns and rows. And this is our nice, there you go. What is it? The decision boundary, right? I want you to pay a very good attention here. We have 3 features, right? When I wanted to plot this decision boundary manually, I got rid of gender, which was male. Is it a good idea to do that? Of course not. So the right way to do that is don't get rid of the feature. Again, what if you have 20 features? You want to get rid of 18 of them? Of course not, right? So what PyCaret is doing is using a dimensionality reduction technique. By default, is using principal component analysis to go from, in this case, 3-dimension to 2-dimension. That's why you see feature 1, feature 2. You don't see what would our feature, estimated salary, or the other one, or age, right? So we see feature 1, feature 2. Feature 1 is a combination of 3 features: gender, estimated salary, and then age, right? Feature 2 is another combination of 3 features, right? So that's a nice thing about PyCaret. Here you go. So this is our decision boundary. Again, for k is equal to 5, it is super flexible. Okay. Then finally, we're going to look into the learning curve. Let me see if I can plot it. There you go. Okay, so it seems that the model is kind of screaming that I need more observations, right? Because the gap is there and it's not shrinking that much. Well, it is. The gap is kind of closing, so maybe we definitely need more observations. But if the gap was constant, no matter how much we are increasing observation, then that was a sign that your model is not flexible enough. It's suffering from high bias. So you have to make it more complex. Even though this is a tuned KNN, right? So this is a tuned version of KNN. So maybe, let's say in practice, you tune the model, you play around with hyperparameters. We did all you could do, and still the learning curve was something like this, and was telling you that the gap is there, the model is suffering from high bias. What should you do? You should change the model. Okay, so you have to use a model which is even more complex or flexible than KNN, depending on the nature of the data, right? So for example, we can do decision tree-based models, random forest, XGBoost, you name it. So those are the models that I'm going to cover in the future videos. All right, so here are some links for you. If you're curious, for example, to know what is ball tree, KD tree, so I can go ahead and click on it. And then I barely talked about it, but the idea is pretty straightforward. Instead of brute forcing and calculating all the distance metrics, go ahead and split the data first, right? So imagine we have these 10 observations. I'm going to split it. This is the ball tree thing, into 2 big balls. So that's where the name is coming from. And then I'm going to calculate the centroid, calculate the furthest points from the centroid, make some other sub balls, let's say, and then based on that, we're going to create a tree. So the idea is that instead of calculating distance between, for example, I don't know, what is the point of interest? Let's say, I don't know, this point, imagine here. If I'm here, just look at the cursor, the idea is that I don't need to calculate the distance between here and all the points that you're seeing. I'm going to go ahead and calculate the distance to point and all the points in the purple circle. That's it, instead of brute forcing. So ball tree, KD tree is using the mode and splitting the space like this, coming up with different. So I just leave it up to you to read it. All right, so we're done with the classification, and I'm going to quickly walk you through to the regression. I think at this point, you can just pause the video and then try to do the regression from scratch on your own. And I highly encourage you to do that, okay? So pause the video and then to go back to the GitHub repository and see, let's see, what is the regression problem? So let's go back here, Python. For regression problem, you're using the wage data set and try, so obviously we're predicting wage by using some features. And go ahead and try to do the k nearest neighbors regression on your own. Trust me, this is a good exercise. And you know all the parameters of the KNN classification, the regression is going to be pretty much the same. Just go ahead and search for a KNN regression, for example, right? And then read the documentation, understand it. Once you're ready, come back, watch the rest of this video, which I'm going to basically fly through the regression pretty fast. Okay, welcome back. This is a regression. So as I said, I'm not going to run this. I just fly over it. So the task is pretty straightforward. You want to predict wage based on all these features. So what I'm doing is basically we're going to clear the data. So for example, for modern education, we're going to fill the NAs with the median values. For further education, we can go ahead and do some sort of regression imputing, right? So what does it mean? So let me pause for a second here. So maybe again, I could have basically gone ahead and then remove the further education because we are seeing 20% of the missing values here. But what if you want to use linear regression to impute the values for missing further education? So what does it mean? It means that you have to come up with another regression model. Let's say you say further education is a function of some other stuff. So I'm assuming that further education is a function of your IQ, your education, modern education, and etc. Again, this is a big assumption, but just for the sake of argument. If that's the case, I'm going to go ahead and create a quick regression line. Remember from our very first modules, we talked about stats model API. So from that stats model functional form API, I'm using OLS, and then I'm creating this simple regression and I'm training it. Now I have a model that I can make some predictions for further education, right? So this is the model. So basically the equation is going to be further education is equal 0.0164 multiply IQ, 0.3291 multiply education, 0.54 multiply modern education, right? So this means that for any observations that we don't have value for further education, go ahead and use the value of IQ, education, modern education, and use this formula, these numbers, to impute the value for further education. That's the whole point, right? So there you go. So we're going to say missing predictions. And basically, we're going to make these predictions only for those values of further educations that are NA, right? So this is what we're doing here. Okay. So these are the values that we're missing. So we are missing 194 observations for further education. And we made some predictions for that because we used a regression. We predicted those observations, right? So basically, pay attention to what I'm doing here. I say, use this model that I trained. Then what are the features? Use these features to make a prediction, but do not make predictions for all further educations. Only make predictions for the ones that further education is NA. Does that make sense? Okay, so, and then I'm gonna add this missing predictions to my NA thing, right? So basically, here was just one example that I wanted to show you that, so for example, what is the prediction for the 6th observation, right? So it's going to be, let's see. Yeah, okay. So here's a data frame without that imputation, right? So further education for 6th observation is missing. Do you see that? Okay. Now I'm gonna say, hey, I'm missing you, so how can I replace this NA with a number? I have a formula which is coming from that regression. It says minus 1.81 this was a constant, plus this is a coefficient, multiply the value of IQ, so it's 116, plus another coefficient, multiply education, plus another coefficient, multiply motor education, which was 8, right? This is what we're imputing, 9.69. So I'm going to go ahead and replace this NA with 9.69. And now we can do it, basically, look at that. I say, go ahead and make this prediction, use the sixth row, right? This is the sixth row. If I do that, I get the same number. You see? Okay. So what are we doing here? We say, go ahead and fill the NA values for further education with what? With these missing predictions. So I put it here. These are all my missing predictions. Okay. This is the sixth one, which was 8.12. Yeah, well, this is 1, 2, 3, 4, 5. So I'm looking at sixth one. Let's look at the sixth one. So let's look at the, oopsie, 8. Sorry, I'm not running this one. So anyway, so if I run, just try to look at the sixth observation. It's gonna be this number. It's gonna be this number that we created. Okay, so cool, that's the imputation. Now the data set is ready. The rest is pretty straightforward. The reason that I wanted to show you this has nothing to do with the KNN regression. This is just a technique in general when it comes to any kind of modeling. When you have a random variable which has many missing observations, so probably you can go ahead and you can make some decisions, right? Should I remove it completely from the model? If it is not that important and you can go ahead and remove it, I would say go ahead and remove it, right? If you're missing 30%, it's not a good idea to impute 30%, right? But if it is something that you're super curious about, right? You're predicting wage and you want to see if your further education has something to do with your wage, you say, yes, I need this one. So let's keep it and let's try our best to impute some value for those missing observations. Again, this is not for KNN regression, it's for any kind of machine learning modeling. All right, so we're gonna scale the features because this is KNN regression. So I'm gonna fly through it. This should be pretty straightforward. I want you to read, again, pause the video, do the code for yourself. It should be straightforward. And then let's see, what do we have? Again, we are looking at categoricals. Obviously, we don't want to scale the categorical variables. That's why these black and married are going to be scaled back to 0, 1s. Now the data set is ready. I can go ahead and basically train a model. So this is KNN regressor. And for KNN regressor, the parameters are pretty much the same. So do I see, if you scroll down, you should see also, yeah, well, let's do it manually. KNN regression, Scikit-learn. The first thing should be the documentation. So what are the parameters? Neighbors, weights, algorithm, leaf size, p, metric, everything is the same. So that's why I wanted to do it on your own, okay? So you make some predictions. So now we don't have probabilities for predictions because remember from the theory lecture, what are these predictions? These predictions are simple average value of the y's, right? So for example, the average value of 2 and 5, something like that, okay? So that's why there's no probability here. So then we can have a nice data frame, actuals versus predictions, and then we can see if they line up, actuals versus predictions in a 45-degree line. So this is not necessarily doing a good job here, but you get the idea because this is a regression, right? We can look at this score. By default, score in regression is going to give us R squared. R squared in the train set, 35%. R squared in the test set, only 6.5%. And yeah, then performance metrics, we can look at the mean squared error. We can do it manually or we can import it from Scikit-learn. It really doesn't matter because MSE is super simple. You can do it this way or you can import it from Scikit-learn, right? So mean squared error. So this is your error, square it, take the average, right? So mean squared error in the test set, mean squared error, and then the root mean squared error in the test set. Okay, again, as I said, you can You can import some of these metrics from Scikit-learn metric as well. We do cross-validation to come up with an estimated number for these things, right? So for example, or for tuning hyperparameter, right? So again, this should be pretty straightforward. So I don't want to make this video longer than this. So make sure you read through this. This should be pretty straightforward, and let me know if you have any questions. You're doing cross-validation, exact same exercise compared to what we had for classification. And then we're going to plot, now in terms of, instead of error rate, we're going to look at RMSE, let's say, or MSE, right? So I'm plotting the MSE of the test set versus cross-validation. So let's say this is the RMSE, this is the MSE of cross-validation. And when for one of these Ks, this is going to be minimized. So it's hard to see it with eyes. So we're going to look at the argmin. So for example, I say, give me the argmin value of this, right? So yeah, that's pretty much it. So let's see. Here, I'm saying that, can you compare the optimal KNN model with multiple regression model? What do you learn? So let's say we came up with K and then we optimized it. And then now we want to compare that performance to this, right? So it seems that the optimal K for, what is it? Yeah, this is our best RMSE in the test set. So here we have a plot. Let's say we have a plot. This is RMSE or the MSE. We're going to take the square root of that, right? So we say, give me the minimum value here. And the minimum value there is this, okay? And we are going to compare it with what a simple linear regression is doing, right? So a simple linear regression is hard to, let's see, 3 digits, 6 digits. Yeah, it's 1,096,000,000, if I'm not making mistakes, 655. Yeah, 1,096,000,000. And this is 1,180,000,000. So it's worse, right? So whatever it is, it's worse. So what did we learn? We learned that for this problem, we didn't need to do fancy KNN regression. Our simple linear regression was doing a better job because it's giving us smaller RMSE. And is it surprising to you? Nope, because remember in regression we talked about curse of dimensionality, right? So we knew that already when the data set is high dimensional. In our case, the feature, how many features do we have? We have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 features, right? So when you have 10 features, it seems that regardless of the value of K, because the dimension for this data set is large, so your model is something like this. So regardless of the value of K, your simple OLS is doing a better job. That's it. This is what we're observing here. Okay. All right. Hope it was helpful. You know, this we could connect the theory with the Python now. PyCaret, again, same story. The only difference is that we are going to go ahead and import everything from PyCaret regression, not classification. Setting up the experiment, their target variable is wage, and then we're pre-processing the stuff. It's going to figure out which one was categorical, which one was not, and etc., etc. And then these are the models for regression. So we have already covered linear regression, lasso, ridge, elastic net. So we already covered these things, and now we are doing KNN. So let's find KNN at this one, k-nearest neighbor regression. And yeah. So we can do, this is our regression model, right? Remember? And for example, if you want to see how we can change the number of neighbors, so you have to quickly read the documentation, right? So I'm going to leave it as an exercise. So you're using PyCaret and you want to see how can we change the number of neighbors. It should be pretty straightforward, right? And okay, we are creating a model PyCaret. This is a performance in terms of RMSE. Let's tune that model and see if we can get a better value. Yes, we did. So the tuned version is a better one now. And we're going to work with that tuned version. So what are the parameters of that tuned version? Again, the distance metric is going to be Euclidean distance, and algorithm is auto, and etc., etc. The weights are uniform, equally weighted. Yeah, we ended up with 49 neighbors, right? So this is tricky. Remember in the documentation for PyCaret in code model container, we saw that k only goes from 1 to 50, and we're stuck at 49, so maybe we needed a higher k. Who knows, maybe we did. All right, so we can do the residual plot. So we have seen these things from PyCaret when we covered the linear regression in module 4, I guess, or 5, module 4, I guess. Yeah, and this is finally our learning curve. Again, it seems that, so here's a good example. Here's a good example, actually. It seems that we have 600 observations, and then no matter how many observations in the train set we have, the gap is not shrinking. When the gap is not shrinking, it says that this is not the right model, right? It has high bias, and probably we don't get a good performance in the cross-validation simply because of the high dimension of the data and things like that. So the lesson learned that I get from observing this learning curve is that, okay, go ahead and change the engine. So we have to go ahead and use another machine learning model. All right, again, in practice, we don't do much KNN regression. We don't use KNN for regression most of the time because there are very simple, even simpler models that are going to perform better. Our friend linear regression is going to do better. As you saw in this example, it did better job. Okay, so that's pretty much it. I hope this was useful, both the classification and regression using PyCaret and Scikit-learn. Until the next one, take care.